The good thing about gas stoichiometry is that it's the same as all other stoichiometry. The coefficients from balanced chemical equation are going to give you ratios, and then those ratios are going to allow you to relate amounts of reactants to each other and amount of reactants to products. We do have an additional advantage with gas stoichiometry, though, and that advantage relates to what we saw in a previous video, and we'll take a look at that in a second. So I've got this problem set up. We want total pressure. After a reaction takes place, we got a 2-liter container, 25 degrees Celsius. In the end, it's still in that 2-liter container at 25 degrees Celsius. So I'm going to highlight right away our volume, 2 liters, that's constant, and our temperature, 25 degrees Celsius and 25 degrees Celsius, that's also constant. And the reason that matters is because when the temperature and the volume are constant, the moles are directly proportional to the pressure. All right? So this is our shortcut. Moles are going to be proportional to the pressure, right? And if you're wondering how that works, you can check out the previous video, or I can show you in lightning round here. If we know PV equals nRT, in this particular case, we're going to solve for n. N equals PV over RT. R is a constant. Volume is going to be constant. Temperature is going to be constant. So you end up with P times V over RT, and that is a constant. So moles are proportional to pressure, is proportional to, if you haven't seen that symbol before, and you can get rid of that proportionality sign by adding a constant, and the constant in this case happens to be V over RT. All of those words, though, are just saying N is proportional to P, and that is the basis for how we're going to do the short version of this problem. So I'm actually going to do the short version first, and then we'll jump back and do the long version, just so you don't have to sit through the long version to get to the short version. First up, to do any stoichiometry, we need a balanced chemical equation. In this particular case, we have hydrogen gas and we have oxygen gas, so this is a reaction that we've seen many, many, many times. I'm going to put it over here just because I know I'll have that space later. We know that hydrogen, 2 of those, and oxygen, 1 of those, give us 2 H2Os. All right? Now, in this reaction, I'm just implying that these are going to stay a gas as a product, which wouldn't be true at 25 degrees Celsius, but whatever. This is our balanced chemical equation. Those are our ratios. Now, the significance of this is we can use pressures to do the stoichiometry. All right? So you could do N equals PV over RT, and you could plug in the pressures that you're given, and the volume that you're given, and the temperature that you're given, and R, which is a constant. But if we know the volume, the temperature, and R, we can just substitute in that pressure. So here's how that looks. We write this out just like we always have done our stoichiometry, what we have. In this particular case, it's going to seem very weird because we have 3.00 atmospheres of hydrogen gas. All right? So notice I didn't put moles or anything like that. We have atmospheres. We also have 4.00 atmospheres of oxygen gas. And now we can do our ratio using our balanced chemical equation. We know for every 2 atmospheres of hydrogen, and you can tell I'm so used to using mole ratios that I forgot we were using atmospheres. The good news is the ratio is the same. There's 1 atmosphere of oxygen. For every 1 atmosphere of oxygen, there's 2 atmospheres of hydrogen, right? And so we end up, in this particular case, needing 3 divided by 2 is 1.5 atmospheres of oxygen, and 4 times 2 is 8 atmospheres of hydrogen. Of quick note to us, we have at this point 3 atmospheres of hydrogen and we need 8. We certainly do not have enough. This becomes our limiting reactant. We have 4 and we need 1.5. This is our excess reactant. All right? We can get an amount excess like we normally do by taking what we have of the excess and subtracting what we need of the excess. So my amount excess is going to be 4.00 atmospheres of oxygen minus our 1.5 atmospheres, which gives us 2.50 atmospheres of oxygen, and that is our excess. It's not the answer to our total pressure that we're looking for, but it's one of the numbers we're going to need. The other thing we need is our theoretical yield, and as you may recall, we get our theoretical yield using the limiting reactant. So as I set this up, I have, theoretical yield, I have 3.00 atmospheres of our hydrogen, our limiting reactant, and I know from my balanced chemical equation there's 2 atmospheres of hydrogen for every 2 atmospheres of water. And we end up then with 3.00 atmospheres of water. And this is my theoretical yield. So I have atmospheres and atmospheres for a theoretical yield, which isn't something you've necessarily seen before. I'm not looking for individual pressures. I'm looking for a total pressure, and we can rely on Dalton's law of partial pressures to get us there. I have 2.5 atmospheres in a 2-liter container at 25 degrees Celsius. I can get that pressure. And so my total pressure will just be the sum of those. Once again, Dalton's law of partial pressures says that the total pressure is the partial pressure of each component pressure, each partial pressure. And in this case, we have the partial pressure of our excess plus the partial pressure of our product. In our excess, we had 2.50 atmospheres. And it doesn't actually matter what they are, because all that matters for total pressure is total moles. And so I'm going to add to it my 3.00 atmospheres of water. Oops, I'm not even going to put the water in there. And we end up with 5.50 atmospheres as the total pressure in our container.